could imagine, does very little of interest. You introduce these minuscule fractions of impurities, and I say minuscule, part in a million, part in a billion atoms. Suddenly, all kinds of exciting things can be made to happen.
The chemist Calvin Fuller developed a highly controlled process for diffusing impurities into silicon. Take phosphorus, for example. It has 5 valence electrons, one more than silicon, and the core has one more positive charge than silicon. If you substitute an atom of phosphorus in a crystal of silicon, the extra electron, carrying a negative charge, will move around in the crystal. Silicon with these extra negative electrons is called N-type silicon. If you add a boron atom, which has one less valence electron than silicon, you are left with a missing electron called a hole. This too can move around in the crystal. Because the hole represents a missing electron, it has a net positive charge. This gives us P-type silicon. Gerald Pearson used Fuller's technique to make silicon rectifiers. He created something called a p-n junction. To make a p-n junction, you take a slab of silicon. You make one side of it N-type and the other side of it P-type. Between these two layers, a transition region develops with a permanent electric force field. Holes drifting into this region will get a kick to the P side and the electrons to the N side. And then something serendipitous happened. Pearson exposed one of his silicon rectifiers to a light source.
He shone some light on a piece of silicon with a p-n junction and discovered that he could get an unknown level of electric current, and realized immediately that this had tremendous implications.
So what was happening? Well, if you shine a light on a p-n junction, you are firing photons at it. Each photon excites one electron-hole pair. The electrons accelerate in one direction across the junction and the holes in the other. All that remained for Pearson was to complete an electrical circuit from one side of the silicon to the other, then shine a light and measure the electric current that flowed. It worked.
What I'm holding in my hands is the first battery, and it states the power that it produces. Not very impressive, but it's the beginning, 1/10 of a watt.
In this modern age, men have at last harnessed the sun with the Bell solar battery.
On April the 25th, 1954, Bell telephone executives unveiled the new power photo cells.
Here are the inventors making a test of their newly harnessed power to operate a small radio transmitter.
This is a demonstration of the Bell solar battery in practical application. Do you hear me? Do you hear me?
And made an enormous impact on the press that understandably went overboard.
They had a huge press conference in New York. They had a light shining on the silicon solar cells, powering a little Ferris wheel that was made from an erector set. And the reporters who came had these great dreams that these little strips of silicon would produce more power than all the uranium, all the oil, and all the gas.
Here, this door was opened, and human imagination could see all kinds of future possibilities. But the first solar cells that were made were enormously expensive, so that the electricity that you got out of it was 1,000 times more expensive than the electricity you got from your standard power station where you burned coal or gas.
So what exactly could the miraculous new power source be used for? Because of their great expense and low power output, early solar cells seemed destined to remain a novelty, powering transistor radios and toys and a few highly specialized applications. The phone company, which had paid for the research, installed solar power experimentally on remote phone lines in Georgia. But was that all it could be used for?
It was just going to be thrown in the dustbin of history when the Pentagon came to Bell Laboratories.
It turned out that there was an application on the horizon right then and there for which the standard sources of electricity out of the question, and solar cells were exactly what was needed. And those were applications for space exploration.
In 1957, the Soviet Union launched the world's first man-made satellite, Sputnik. It caused consternation in the US. The Soviets were in the lead in the so-called space race. But Sputnik stopped transmitting after several weeks for the simple reason that its batteries ran out. So, what was the alternative?
There were a variety of power sources, but they all died out over time. The batteries had to be recharged in some way, and they couldn't be recharged. It was a natural for solar energy. The satellite is up there in the sun all the time. Even if it's inefficient, there's energy that you can count upon. It was proof that this is a viable technology. It lasted longer than the satellites. This was the beginning of the new age of solar photovoltaic effect.
The eagle has wings.
By the time we went to the moon 10 years later, it was accepted wisdom that solar or photovoltaic cells were the best way to go.
The solar panel industry at that time for space was like a jewelry business. All the parts were made by hand, they were inspected multiple times. There were 300 steps in making every one, and each solar panel is a work of art. It's very special.
Reliability and durability were, and still are, the overriding requirements in space. The cost of solar panels is insignificant compared to the overall cost of a satellite. Today, solar-powered satellites connect vast numbers of communications networks. They coordinate transportation. They keep us informed on television. Nearly every cell phone call passes through solar-powered equipment. Modern life would be unthinkable without it. But down here on Earth, the bean counters are more rigorous. If solar is to be an option, it has to be more convenient or cheaper than what's already on offer. That's why, ironically, it was the oil companies that became the first major industrial users of solar power. Offshore oil rigs need electricity to run warning lights and horns, and there's no power grid out at sea. Solar panels combined with small storage batteries made practical and economic sense to the Coast Guard, too. Today, 99% of all their navigation aids, including lighthouses and buoys, rely on solar electricity. The more remote the location, the greater the need for photovoltaics. Railroads power distant switches and signals with solar panels. The phone company powers microwave relay stations in the mountains. And airfields can operate 24 hours a day wherever they are, thanks to handy devices like these self-contained blue landing lights.
A simple solar panel, the mountains are an excellent place to collect solar activity, and they use LED lights on the interior of the lens. A phenolic lens distributes that small amount of light to make it look like a regular taxiway light.
Here at California's Truckee Tahoe Airport, it would have cost them more than $1 million to connect their lights to the grid. Solar units cost just $135,000.
We also reduced the time for installation from 2 years to 1 month. In addition to that, the ongoing savings is about $18,000 a year.
The future of solar power for remote installations looks good. But will it become a major part of the world's energy mix? That depends on people like Terry Jester. She's worked in photovoltaics since the 1970s.
It was just an amazing time to be part of a group of people working 80, 90-hour weeks, feeling so committed and feeling like what we were doing and what we could do would change the world and change the future.
Terry Jester is Director of Operations at this factory, which is now owned by Shell. It has been making solar panels for more than 25 years. The whole time, the primary target has been to cut costs.